Hi, I'm Justin Hensley, and this is the first in a series of videos where I'll be talking about OpenCL. I'm a senior member of technical staff in AMD's Office of the CTO, and in particular I work on advanced technology development. And for about the past 10 years I've been doing what is called GPGPU, or general purpose computation using graphics processors. And so today what we're going to be talking about is what is OpenCL and why was it designed the way it was designed. So with OpenCL you can leverage CPUs, GPUs, or even other processors such as the Cell Broadband Engine or DSPs to accelerate parallel computations. So the key point here is that we're accelerating parallel computations, not sequential computations. And for things that are computationally intensive, you can get dramatic speedups. And one of the goals of OpenCL is to write portable code that'll run across all sorts of processors. So you can write your code once, have it run on a CPU, a GPU, a DSP, or any number of accelerator devices. With AMD's OpenCL, you can leverage AMD CPUs and AMD GPUs to accelerate parallel computation. In today's video, we're going to talk about the design goals and the execution model of OpenCL. In later videos, we'll talk about the memory and platform models, how to allocate resources, and the actual programming language used in OpenCL, which is termed OpenCL-C. So the execution model. There are three basic components of OpenCL. The first is we have kernels. Kernels are the basic unit of executable code. So this is very similar to a C function. They can be data parallel or task parallel, but the key thing is that they're parallel, and we're using OpenCL to exploit parallelism. The next key fundamental unit would be a program object. So programs are collections of kernels and other functions, and you can kind of think of these as a dynamic library. So we could write some set of functions that would be called kernels. Those kernels would be grouped into programs, and these programs would be called from your application. Finally, applications queue kernel execution instances using what are called queues in OpenCL, and these are queued in order and executed in order or out of order. Let's first talk about how can we express data parallelism in OpenCL. So let's say we want to define an n-dimensional computation domain. So that could be where n is equal to 1, 2, or 3. So let's say n is equal to 1, that would be a vector. So we have just a one-dimensional array. If n was equal to 2, that's something like an image. So let's say we're processing an image. Or if we wanted to process a volume, that would be n equal to 3. Each independent element of our execution domain is called a work item in OpenCL. So the n-dimensional domain defines the total number of work items that are executed in parallel. So let's say we wanted to process a 1024 by 1024 image. That would be our global problem dimension. And we would have one kernel executed per pixel. So each pixel would correspond to a work item in OpenCL. If we look on the left side of the slide here, we'll see some scalar code to do some processing on an image. And so if you were writing very simple C code, what you would do is you would write a simple for loop. And in this for loop, you would go from 1 to n, and then you do some computation. So an alternate way of doing this would be to do it in a data parallel fashion. And in this case, we're going to logically read one element in parallel from all of A, multiply it from an element of B in parallel, and write it to our output. So you'll notice that in the code segment on the right, there is no for loop. We just get an ID value, we read a value from A, multiply it by a value from B, and then write the output. It's key to note that kernels are executed across a global domain of work items. Our global dimensions define the range of computation. One work item per computation is executed in parallel. But we can further group our global domain into local work groups. And so our local dimension tells us the size of our local work group. And these are executed together on one device. And the reason they're executed together on one device is that way we can share local memory and synchronization. Because the whole point of OpenCL is to let us use highly parallel devices to accelerate computation. So when we group our domain into work groups, we know that those work groups will be executed together and they can share resources and collaborate together. So there's some caveats though. Global work items must be independent. So there's no synchronization between global work items, only between work items within a work group. Synchronization can only be done within a work group. And if you want to synchronize on a global scale, you have to do that on kernel boundaries. So let's look at this global and local dimensions a little bit further. So let's say we're going to process an image. And that image is, again, a 1024 by 1024. So that's the whole problem space of this image that we're processing. So again, 1024 by 1024 will be the global dimensions of our problem. And in this case, let's say we've decided that our local problem size should be 128 by 128. So on the bottom of this slide here, you can see there's an image of an eye, and the width and height are depicted. So what's going to happen is that we're going to process this global problem in chunks of 128 by 128, depicted by the transparent blue squares. So we'll block up this large image into small work groups that are processed. And the important thing to note is that for a single work group highlighted right now, we can actually synchronize between those work items. So we can use barriers or memory fences to allow those work items to actually communicate with each other. But if we look at two work items that are not in the same work group, such as that are highlighted now, those cannot synchronize with each other because they are not in the same work group. Some example problem dimensions. Let's say we wanted to process 1 million elements in an array. In that case, the best choice might be to have a one-dimensional n-dimensional domain. In that case, we're going to have a 1 million by 1 by 1. There are other situations, let's say you're processing a HD video frame, that you might actually want to do 2D dimension. And in that case, we might do a 1920 by 1200 by 1. And that just so happens that when we're processing images, that's the best domain that we want to use. But let's say you want to do some volume processing. In that case, you might want to do a 256 by 256 by 256 global size because it maps well to the problem. So with OpenCL, you want to make sure that you choose the best dimensions that map to your problem and also give you the best performance. Let's go back to the synchronization within work items. So there is no global synchronization that's only within work groups. So each work item in a work group can use barriers to synchronize execution, or it can use a memory fence to synchronize memory accesses. Note there are two different ways to actually synchronize work items in a work group depending on what you're doing, whether you want to synchronize execution or memory accesses. You must adapt your algorithm to only require synchronization within work groups. So let's say you're doing a local reduction, and in that case, you're using barriers or memory fences, or between kernels. And so in that case, if you really need global synchronization, you have to do a multipass algorithm because the only way you'll be able to synchronize is between different kernels. So expressing task parallelism in OpenCL. So we just talked about how do you express data parallelism in OpenCL. It's also possible to express task parallelism in OpenCL. And here what we're going to do is we're going to execute a single work item as a task. And you can write your kernels either in OpenCL-C, which we'll be talking about in a later video, or as a native C, C++ function. You might be asking yourself, why would I ever want to express task parallelism in OpenCL? Well, the important thing is OpenCL has a fairly robust event model. And so that allows us to actually use the OpenCL event model to have task parallelism and data parallelism working together to fully utilize the entire system that you have. That's it for today's video. I appreciate you listening, and I hope you listen to the further videos where we'll be talking more about OpenCL and OpenCL-C. Once again, this is Justin Hensley. Thank you.